So today I have the great pleasure to introduce François Golse. So François Golse is a professor at the École polytechnique since 2006. Before that, he was a professor at the University of Paris Diderot. He did his studies at the École Normale Supérieure, and then he obtained his doctorate under the supervision of Claude Bardos at the Université Sorbonne Paris Nord. I don't think it was called like that before. I don't remember. François is a specialist in partial differential equations, focusing mainly on classical and quantum mathematical physics equations. So he authored almost 200 publications, and in his career, he did several breakthroughs in the field. For example, let me mention just few. Let me mention the averaging lemmas for kinetic equation, and the hydrodynamic limits for the Boltzmann equation, and the Boltzmann-Garat limit for the two-dimensional periodic Lorentz gas, and then classical and quantum mean-field limits, and much more. For his work, he received several honors. For example, he was co-winner in 2006 with Laure Ramon of the SIAM PDE prize of SIAM for a best paper in partial differential equations. So you have already a long history with SIAM. Then he was plenary speaker at the European Congress of Mathematics in 2004, and invited speaker at the International Congress of Mathematicians in 2006 in Madrid. He is honorary member at the Institut Universitaire de France, of which he has been member from 1999 to 2004. He received the Louis Armand Prize for the French Academy of Science and gave one of the PECO lectures at the Collège de France. And I think that's a big resume, I don't know. But today we will talk about quantum dynamics and optimal transport.
Well, thank you very much for this grand introduction. All right, so I wish to first thank the organizers for inviting me to this SIAM seminar. I'm so happy to see so many of you, even though it's in remote mode, but well, nevertheless, I'm very happy to be here with you. And so today I'm going to talk about application of ideas from optimal transport to quantum dynamics. And things I want to discuss are based on papers with Emmanuel Caglioti, Shijin, Clément Mouhot, and Thierry Paul over the past 6 or 7 years. All right, so let me start right away with, let me start right away with a quick description, quick background of what I mean by quantum dynamics, well, you don't have to know much in quantum mechanics in the first place because I don't know much myself. So yeah, I mean, you don't need to know much. All right, so classical mechanics for a point particle of mass m with position q of t, momentum p of t in Rd, can be described in many ways, but in particular, it can be described by the Hamiltonian picture where you have a function h of qp, which is the sum of the kinetic energy, normal p squared divided by 2m, plus the potential energy, v of q, to give the total energy. And once you have the total energy in this form, you write, you obtain Newton's second law of motion in Hamiltonian form. Like so, you write q dot of t, time derivative of q, equals p of t over m, which is del h del p. And p dot of t is minus del h del q, which is minus the gradient of v at the point q of t. So this is the motion of a single point, but if you like PDEs, and if you more interested in probability density of finding your point at the position x and with momentum psi at time t, then you want to write the Liouville equation, which is written here in full glory. So del t f of tx and psi plus 1 over m xi del x f minus del v of x del psi f equals 0. And here you recognize in this underlying expression the Poisson bracket of this Hamiltonian h with f at time t viewed as a function of x and psi. Good, so that's for classical mechanics of a point with mass m. Now for quantum mechanics, you also have a Hamiltonian description, which is the following one. So instead of looking at a position and momentum, you look at a new object, which is a wave function, psi, which is a complex valued function of t and x, where x now is the position and lives in Rd. So this L2 of Rd with value in C, I will denote by Gothic H, and I will usually require that wave function satisfies the normalizing condition that psi at time t, if you take the L2 norm, should be equal to 1. Okay, so like before, you have a Hamiltonian, which now is going to be a quantum Hamiltonian, which instead of being a function, a real valued function on phase space, is going to be an unbounded operator on Gothic H, but it's going to be a self-adjoint unbounded operator on Gothic H, which is given by the sum of the kinetic energy, which here is going to be minus h bar squared over 2m Laplace x, plus v of x, and you think of v of x as being the multiplication of an element of Gothic H by the function v of x. So here you see, if you want to pass from the classical Hamiltonian to the quantum Hamiltonian, the idea is that you have this correspondence principle, as it's called, which replaces the function v of q, the potential energy, by the operator on Gothic H, which is the multiplication by v of the current variable, say x, so it's multiplication by v of x. And if you look at the components of the momentum, pj, you want to replace it by minus I h bar, Planck constant, times del xj. And it's usually a good idea to replace minus I del with the capital T. I mean, I will use this notation here systematically. All right, so now with this, the analog of Newton's equation, which is a system of ODE, comes as a PDE, which is Schrödinger equation, IH bar del T psi equals H psi. And now, because H is a self-adjoint operator, now if you multiply it by I, becomes a skew adjoint operator. By Stone's theorem defines a unitary group on Gothic H, and therefore psi at time t is going to be this unitary group e to the minus ith over h bar acting on psi at t equals 0. Equivalently, or more generally, I should say, the equation that corresponds to the Liouville equation in classical mechanics is going to be the von Neumann equation for objects which are slightly more general than a single wave function. For instance, if you take R of t to be the projection on the complex line spanned by psi at time t, but you can have much more operators. This is just one example of an operator. Then you can look at the equation IH bar del t of R of t equals to the commutator of H with R of t. So here you have a bracket, which is another type of bracket than the Poisson bracket, but nevertheless, you see here that you have the same structure, pretty much the same structure as in the case of the Liouville equation in classical mechanics. And here you propagate this R of t by conjugation with the unitary group generated by your Hamiltonian H. Okay, good. So now there is a very classical estimate in classical mechanics, which is called pair dispersion, among other things. So consider classical dynamics of your favorite point with mass 1. And here I'm going to call L the Lipschitz constant of grad V. So I'm going to assume that that the force deriving from V is Lipschitz continuous, and I call L its Lipschitz constant. And then suppose I look at two different trajectories of my Hamiltonian system, one which is x and psi. So you have a solution of this ODE system here, another one which is y and eta. So you have y dot equals eta, eta dot equals minus del v at y. And then you can check, it's a very easy computation, that if you take the time derivative of the distance between x psi and y eta, square distance, Euclidean distance, this is less than or equal to 1 plus L times that same distance here. So immediately you see you're going to have a Grunwald inequality, which tells you that this quantity here is going to grow at most like exponential of 1 plus LT. In quantum dynamics, because H is self-adjoint, the Hamiltonian is self-adjoint on L2. If you look at two different solutions to the Schrödinger equation, H bar del T of psi 1 equals H psi 1, and H bar del T psi 2 equals H psi 2, by linearity, you can look at the difference between psi 1 and psi 2. It's still a solution of the Schrödinger equation, because the Schrödinger equation defines a unitary group on L2. Then you have that the time derivative of the L2 norm of the difference psi 1 minus psi 2 at time t, here to the square, this is equal to 0. So in other words, the L2 norm of the difference between psi 1 and psi 2 is a constant of the motion. It's independent of time. So this is, you might say, this is very nice, because you have a uniform in H bar estimate of the difference without having to assume any regularity on the potential. I mean, obviously, to have this estimate here, all you need is that H is a self-adjoint operator on L2. And certainly, if you take like V bounded, for instance, it's going to be a bounded perturbation of the Laplacian, which is a self-adjoint unbounded operator on L2. You add any bounded perturbation thereof, it's going to be, and real valued, of course, it's going to be, again, self-adjoint. And so you see that in order to have this estimate, right, that the L2 norm is a constant of the motion, you need much less regularity than in the classical case, than for classical dynamics, where you need, for instance, if you want to define the dynamics, then you need that V has a Lipschitz continuous gradient if you want to apply Cauchy-Lipschitz. Good. So this looks nice, but since you expect that quantum mechanics in some limits tends to or converges to classical mechanics, you suspect that there is going to be a slight problem somewhere. And the slight problem is in the quantity or in the way that you measure distance between quantum states. So let's look at a particularly interesting case, which goes by the name of the Schrödinger coherent state, also called the wave packet or Gaussian wave packet, centered at QP in RD. So Q is the position, P is the momentum. So what is it? So you take a plane wave at frequency P over H bar, so this is the wave vector, and you modulate it by a Gaussian of width square root of H bar. So this is the object, right? So you can check that this is a normalized wave function. And now you can look at the squared L2 norm of the difference between these two wave functions. So if you compute it, this is not a very complicated computation to do, then you find this is equal to this quantity here. Maybe I made a mistake somewhere, but an essential mistake, because all that matters is that if you look at this quantity here and if you let H bar go to 0, then you see that the exponential here is going to disappear. The cosine, no matter what, is less than 1 in absolute value. So this quantity here is going to converge to 2 if the 2 points in phase space, Q1, P1 and Q2, P2 are different. It's obviously equal to 0 if these 2 points coincide. So in other words, in the limit as H bar tends to 0, this Q1 P1 minus Q2 P2 squared is going to converge to the total variation of the difference between Dirac at Q1 P1 minus Dirac at Q2 P2. And since you believe that this quantity here is one quantum analog of Dirac in phase space, then the L2 norm is going to converge to the trivial distance. And in particular, it will fail to capture phase space distances larger than anything of the order of square root of h bar. So for the classical limit, this is not a very nice object. So here I'm going to use systematically in the sequel the Dirac bracket notation, which I've recalled here. So the reason for introducing this trench notation for this wave packet is that this is viewed as a vector in Gothic H in your Hilbert space, whereas the bra, like here, is simply the same vector, but viewed as a linear functional acting on Gothic H. So yeah, I mean, this is the bracket notation, which is quite convenient, used by physicists, but I think equally convenient for mathematicians. Very good. So the L2 norm, in spite of being very nicely propagated, has some deficiency, which is explained here. Yeah, so here for your convenience, I've drawn some examples of some pictures of these wave packet. So this is the oscillating structure of a Gaussian wave packet. So you see that the thing oscillates much faster, right, than the wavelength of the Gaussian amplitude, which is here. If you look at the 3D picture, so here the idea is the following one. So the center of this bump here is going to be the position. And if you look, you have these wrinkles here. And these wrinkles, they define a front, right? And these, the vector orthogonal to the front, which in this case is this vector here, is the direction of the momentum, right? So this is your vector P. Good, so this is how you can think of a Gaussian wave packet. So the structure of the oscillations define the momentum, and the center defines the position. So you encode both with one single function. Of course, a rapidly oscillating function. Good, so now let's come to the first part of the title, which is optimal transport. I'm not going to talk much about optimal transport, but about some ideas of optimal transport and how you use them in the context of quantum dynamics. Good, so optimal transport starts with paper, actually a memoir, written by Monge shortly before the French Revolution. And if you read here, if you know enough French to read here, he is speaking about moving material from one place to another. And he explains here that the price of transport from a molecule, but which from Monge means some lump of mass, is proportional to the weight and to the distance, which is a statement. Okay, so you can think of other way of pricing the transport. And actually, in this talk, I'm going to use a different pricing strategy. I'm going to assume that it's proportional to the square distance, right, and not to the distance, which was Monge's original idea. So if you use this square distance pricing, then the Monge optimal transport problem can be written in the following manner, right? So the idea is that, of course, if you take 2 points in the Euclidean space, obviously the Euclidean norm, x minus y squared, discriminates better Dirac at x and Dirac at y than the total variation, because the total variation just is going to tell you whether x is equal to y or different from y, but doesn't measure the distance between x and y. So here, the Monge problem was initially that if you want to move mass, and suppose that you start with a probability measure, modern mathematicians want to think about probability measure, like this, 1 over n, the sum of the delta at xi, and you want to move this mass to another location, which is, for instance, 1 over n, the sum over j of Dirac at yj. I mean, this is just an example. Of course, you have many more possibilities. But anyway, let's look at this example here. Then the Monge problem, provided that you replace the price of transport by the square of the distance, is going to be the sum over I of xi minus y of sigma of y, because of course you can relabel the yj arbitrarily, and then maybe the best strategy is not to transport x1 on y1, x2 on y2, etc. And you want to minimize over the set of permutations. Okay. Now, this is not a particularly nice problem if you write it in this way. So what Kantorovich did, he did a relaxation of the problem, which means that you generalize this minimization problem by, in this manner, you look at the minimum from ij, of the sum from ij equal 1 to n of aij xi minus yj squared, where the aij are the entries of a bistochastic matrix. So all the coefficients are positive and the sum of the rows and columns is equal to 1, right? So obviously here, this case corresponds to the case of a permutation matrix. And the idea is, of course, Monge's idea, except for the square, is to use the square root of MC to measure the difference between these two empirical measures here, right? So here, this is a discrete case. So if you want to look at a continuous setting, then you call, I'm going to denote by P of RD the set of Borel probability measures on RD. I'm going to denote by P2 of RD those probability measure which has finite second order moment, right? So which is this definition here. I'm going to call a coupling of mu and nu, which are two probability measures on RD, a probability measure on the product of RD with itself, on the product space where these two probabilities live. And what I want is that if you take pi and if you average out the variable y, for instance, you should find mu. And if you average out the variable x, you should find nu, right? So if you want to write this with test function, this is the identity which is written here. The integral of phi of x plus psi y pi is equal to the integral of phi mu plus the integral of psi nu. Good. And so this has to hold for all phi and psi continuous bounded functions, say. So the set of couplings of mu and nu I'm going to denote by C of mu and nu, C as coupling, and it's always non-empty because it contains mu times nu, which is usually not a very clever coupling, but this has the merit of being at least one coupling, and therefore C of mu nu is not empty. And with this, then you can look at the minimization problem, which is here. You look at the minimum of the integral of x minus y squared integrated with respect to pi, and you minimize over all the couplings of mu and nu. Turns out that this infimum is a minimum. It's finite because you have this measure here in among the couplings. And so you take the square root of this, and this defines a distance on the set of probability measures with finite second order moments. Good. So that's the Wasserstein, Monge, Kantorovich distance, whatever you want to call it. Here it will be denoted by W2. How can we define such an object in the quantum setting? Okay, so now the object that replaces probability measures is going to be density operators. But before I define density operators, let me define the analog of integration in the quantum setting, which is the notion of trace of an operator. For those of you who are not familiar with trace class operators or don't like this, let me recall one possible definition. If you take T equal T star, a non-negative operator on Gothic H. And if you take any Hilbert basis of Gothic H, then you can look at the quantities, sum of En in a product with TEN in H, sum over N. This quantity is non-negative, possibly infinite, but you define this to be the trace of T, and this is independent of the Hilbert basis which you choose. Good. So your operator T will be trace class if this is finite. Otherwise, it will not be trace class. that's life. It's a little bit like when you define the integral of a positive measurable function, right? So that's the similar definition. So now with this definition of trace, I'm going to define the density, a notion of density operator on the Hilbert space Gothic H, which here is going to be L2 of Rd. So a density operator on Gothic H is going to be a self-adjoint non-negative operator on H, bounded operator on H, right? Such that its trace is equal to 1. So the fact that it's self-adjoint means it's equivalent to saying that you have a function that is real valued, that it's non-negative is equivalent to having a non-negative function or non-negative measure. And taking the trace equal to 1 means that the integral, this is the analog, assuming that your function or your measure has total mass equal to 1. In other words, that you have a probability density or probability measure. There is the thing that is analogous to this P2 object. Probability measures with finite second order moments. In the quantum setting, it would be convenient to look at D2 of Gothic H, which is going to be the set of densities on Gothic H, whose such that the trace of square root of R times the harmonic oscillator times square root of R is finite. Okay, so this is obviously a non-negative operator. What you just require is that this operator is trace class. Okay. So in particular, if you look at the orthogonal projection on Schrödinger coherent state QP, this is an example of density operator, right? So it belongs to D2 of Gothic H. So now the analog of coupling in the quantum setting, you're going to call a coupling of RS density operators on H, L2 of Rd, is going to be the set of density operators in H tens H, but here at H tens H, if you don't like tensor products, think it's just L2 of Rd cross Rd. I'm just doubling the space of position variables, right? So this is Q, a density operator on L2 of Rd cross Rd, satisfying the analog of this condition, which is here. And the analog of this condition is the fact that if I take the trace on H tens H of Q times A times I, which is the analog of a function that depends only on the first variable, plus I times B, this should be the trace of RA plus SB, exact analog of what I wrote in the classical setting. But here I replace trace, I replace the integral with the trace, and I replace continuous bounded functions with bounded operators. Voila. Good. So now, in order to define a distance, sorry, what is this? Yeah. Let me see. Yeah. So now I have to define a transport cost. Okay. So I remind you of the correspondence principle. The correspondence principle in quantum mechanics tells you that if you look at the function Qj, the correspondence principle associates to it the multiplication by xj, which is a position variable in L2 of Rdx. Okay. And Pj, the function Pj in classical mechanics, momentum, the jth component of the momentum vector, goes into minus I h bar del xj. In other words, to h bar dxj, capital D xj. Right? So here you have functions of Q and P, functions of the coordinates in phase space, which go into operators, possibly unbounded, here in these cases, unbounded operators undoubtedly, but operators in L2, operators acting on L2 of Rd, which is our Hilbert space. So with this correspondence principle, you can think of the quantum analog of the square phase space metric, which if you take two phase space points, say PQ and P hat Q hat, the metric, the distance between these 2 points in phase space is going to be P minus P hat norm squared plus Q minus Q hat Euclidean norm squared. And so the quantum analog of this, you replace Q by X, P by minus I H bar del X. And here's what you get. You get a differential operator, C of X, H bar dx, X hat, H bar dx hat, which is self-adjoint and bounded but self-adjoint, and which is given by this formula here. So if you want to write it in coordinates to be sure, so this is the sum over j from 1 to d of xj minus xj hat squared minus h bar squared del xj minus del x hat j squared. So if you want, this is a harmonic oscillator in the variables xj minus xj hat. That's what it is, simply, right? It's a sum of harmonic oscillator in each independent variables. And you know that each of these operators, these are the Heisenberg inequalities, each of these operators are bounded below by 2 h bar times identity. And so at the end of the day, this operator here is bounded below by 2d h bar identity on h tends h. Good. And with this, you can define a quantum Wasserstein pseudometric. I call this a pseudometric because we're going to see very quickly that it's not a bona fide metric. So I define Gothic d of R and S equals to the square root of the infimum over all couplings of your density operators R and S, other trace of square root of Q, which you define by functional calculus, times your operator C, which you've defined here, times Q1/2. You take the trace and take the square root, and that's your Gothic d of R and S. Yeah, observe that if you compare this to the expression in the classical case, let's see, where is it? So you have this expression here, and so the thing that corresponds to Q is pi, but here pi is just on one side of x minus y squared. But in the classical picture, you have functions, measures, these things are commutative. Here, it's more natural to look at this quantity here, because this quantity is going to be self-adjoint, non-negative operator, right? So it's more legitimate to look at this quantity here, putting square root of Q on each side of C. Good. Of course, if C would be for a bounded operator by the cyclicity property of the trace of AB equals trace of BA, means that you could move Q on this side. But here, I'm not saying that CQ is trace class, right? So it's a slight difficulty, or slight subtlety in this definition. Good. So what are we going to do with this? Okay, so here I've recalled the correspondence principle by this prescription here, and I want to go more into this correspondence principle to say a few things more about this correspondence principle, because here I have defined a very nice pseudometric, but we don't know much about what can be done in terms of computing this pseudometric and what are the properties of this metric, etc. This is so far pretty abstract, say. Good. So I recall Schrodinger's coherent state, which is this wave packet here. So that's the formula. And so now, if you give me a probability measure, by probability measure on phase space, out of this, I'm going to define a non-negative operator, which is going to be, in fact, a density operator on Gothic H, which is my L2 of RD space, by this prescription. So what I do is I take the orthogonal projection on QP, which is this Schrödinger coherent state, and I take the superposition of these orthogonal projection, which I average with respect to the measure mu. And so I have a map which to mu associate a density operator on Gothic H on L2 of RD. Okay, so I have a map which associates to any probability measure to any classical density a quantum density. Conversely, if you give me your favorite density on Gothic H, I can evaluate this density, call it R. So I apply it to QP, to this coherent state. That's a function of which I take the inner product with QP, right? So I evaluate R on the state QP, divide by 2 pi h bar d. So that's a non-negative quantity, and you can check, this is an easy computation with the Fourier transform for Gaussian, that the integral of this quantity in dp dq turns out to be the trace of R. So in other words, this is equal to 1 because R is a density operator. So this thing goes by the name of the Usimi transform, right? And the idea is that these Usimi and Toplitz maps are almost inverse of each other in the sense that if you take probability measure mu, you take its Toplitz transform script t, and that defines an operator of which you can take the Usimi transform, and the result is almost equal to Q, except that it's just Q on which you let the heat flow in phase space, but at a very small time, h bar over 2. I mean, if you're in a setting, of course, where h bar is small, right? So for h bar small, this, if you want, is close to mu, but of course, is going to be much smoother than mu, of course, right? So this is a smooth approximation of mu. But of course, for h bar very small, you can think of these as being almost inverse to each other. Okay, so with this, I've recorded on this slide, short of being able to give you computations of these pseudometric, and after all, you know, computing even the Wasserstein distance, the classical Wasserstein distance, it's usually not an easy matter. But here are what the thing that you know. The first thing is that this Gothic D of R2S for all densities is bounded below by square root of 2d h bar. So that's just because the transport cost is always bounded below by 2d h bar identity, right? So when you trace it with respect to any coupling, the result is always larger than this, okay? In particular, where R equals S, this quantity is never equal to 0, okay? Good. Now, if you take mu and nu, which are probability measures on phase space with finite energy, then this pseudometric between the Toplitz of mu and the Toplitz of nu, this is controlled by the Wasserstein distance squared from mu to nu plus 2d h bar. And in particular, you can check with A that the Gothic D of T of mu to itself is equal to square root of 2d h bar, right? So this is a consequence of A and B. Okay, so you have an upper bound for Toplitz densities. You also have a lower bound for arbitrary densities in the following form. So if you pick your favorite densities with finite energy on Gothic H, then the square of the distance, Gothic D of R to S squared, this is bounded below by Wasserstein of Usimi of R to Usimi of S squared minus 2d h bar, okay? All right, so these are estimates to within an error of the order of square root of h bar, obviously. However, there is one example where you know how to compute exactly the distance. If R or S are rank 1 projections, then for rank 1 projections, you have only one coupling, which is the trivial coupling R times S. And so in that case, you have this formula for the Gothic D from R to S. Okay. What can we do with this? What am I doing here? This is very strange. Yeah. All right, so as I said, this is a pseudometric, and the pseudo means that it's not quite a metric. Let's nevertheless investigate the metric properties of Gothic D. So here, in this previous slide, I have compared Gothic D to something that's a nice metric, which is namely the Wasserstein metric of exponent 2. Let's now look at the metric properties of Gothic D itself without any such comparison with the Wasserstein metric. So as I said, it's relatively easy to check that Gothic D of R to S is always bounded below by the square root of 2D H bar. It's also relatively easy to check that it's a symmetric function. So Gothic D of RS is equal to Gothic D of SR. Very good. But we know that Gothic D of RR is non-negative, and though therefore Gothic D is not a nice metric on D2 of Gothic H. But when H bar tends to 0, it maybe looks like Wasserstein 2, okay, in some sense. Okay, so anyway, so it's not a metric. We have to live with it. Let's think about the next property we could expect of bona fide metric, which is the triangle inequality. Okay, so for the triangle inequality, here is what we have. So we have a sort of generalized triangle inequality, which is written here. So if you take any RST density operators with finite energy, then you have the triangle inequality up to an error square root of dh bar, right? So the distance from R to T is less than distance from R to S plus distance from S to T plus square root of dh bar. In particular, it's less than or equal to the distance from R to S plus the distance from S to T plus 1 over square root of 2, the distance from S to S, which is never equal to 0 by this inequality here. But if the rank of the middle point, S, is equal to 1, then the honest triangle inequality holds whatever R and T, right? So you just need that the middle point has rank 1. So I'm looking at this inequality here, which is a consequence of the first one, because there is another notion of quantum Wasserstein distance, which has been proposed by De Palma and Trevisan, which appeared in Annals of Henri Poincaré 2021, so last year, where you have, so it's a different object, but you have a similar triangle inequality here with the distance from S to itself. So in other words, you have to think at this, you have to think at a geometry where points, if you want, have a thickness so that it costs you something to travel from a point to itself. So it's a very strange thing, but that's the way it is. Good. All right. So these are the metric properties of Gothic D. I don't know whether the true inequality, true triangle inequality is true for Gothic D. But I mean, this is the best I can do. This is the best we know at the moment, right? All right. So can we compare optimal transports in the quantum and in the classical setting more precisely than through these inequalities which are here, right? I mean, for instance, are these inequalities strict or not, right? So what do we have in this direction? All right, so there is an observation which we got with Emmanuel Caglioti and Thierry Paul in Rome in 2018, which came out last year. So you have the following observation. Suppose that you want to do optimal transport, and here I'm going to assume that the momentum is 0, right? So I'm going to look at a probability measure that's simply 1/2 of Dirac at the position A plus the Dirac at the position -A and with no momentum. And I want to move this to 1/2 of Dirac at plus B plus the Dirac minus B, and again, no momentum. Okay, so if you look at the classical picture, you have 2 points, x1, x2, y1, y2, and you have equal mass on these 2 points. And the optimal transport in the classical setting is you move x2 to y2, x1 to y1, you move mass 1/2 in both cases. Right, so then in that case, you can compute, this is not completely trivial computation, that in this case, the quantum distance between the Toplitz operators built on mu and nu turns out to be exactly to the square, turns out to be exactly equal to the Wasserstein distance between mu and nu squared plus 2h bar. So in other words, here, this inequality here becomes an equality for this case. Very good. So here, essentially, you are in a situation where that's the quantum transport costs you up to this 2h bar, which counts for nothing. This optimal transport on the quantum side is exactly the same strategy as on the classical side, right? So it's the same procedure. You move this to this, you move this mass to here, and this mass to there, and voila, right? So in other words, you can summarize this by saying that the optimal coupling between T of nu and T of nu is going to be the Toplitz map, the Toplitz operator, with which is based on an optimal coupling of the two measures, right? So you simply take the measure, take the classical coupling, and you quantize it by Toplitz quantization. So is this a general feature? That would be a bit depressing, because it means that you don't have anything new if you look at the quantum picture, but fortunately not. And now suppose that you look at another problem where you have the same location, right? So you're moving, you have the same location, plus and minus a, right? Plus and minus a, but you have different masses. Here you have 1/2, and here you have, say, 1 plus epsilon over 2, 1 minus epsilon over 2, okay? So here, the classical setting is very clear what you have. You move all the mass from x1 to y1, you move 1/2 from x2 to y2, and you move the remaining mass from x2 to y1, and that's it. Is that what you see in the quantum case? No, not at all. And in fact, quantum optimal transport is cheaper, because if you look at the Gothic D between these two Toplitz densities, this is strictly below the classical cost. Of course, modulo the 2h bar quantum factor, additional term. And the idea here is that if you look at the optimal coupling in the unequal mass case, includes a Toplitz coupling, like the one I described before, which is given by this blue picture. This is the thing that has a classical interpretation, but it includes a non-classical contribution where these tau, k, l, and n involve tensor products here, which are it's not the same. K and L is not equal to M and N. And therefore, these corresponds to terms which have no signification, no classical signification. Of course, this is a term of order h bar, but this is a purely non-classical contribution, which appears as h bar tends to 0. But nevertheless, for finite h bar, it's there, and it accounts for the difference, which is here. Okay, so in other words, to summarize, if you move from classical to quantum couplings, then of course you have more couplings. But it could still be that the optimal strategy leaves you inside the set of classical couplings. Well, this is not the case in this particular example here, where you have to move different masses. So in general, you could expect that it's not going to be the case at all in general. Okay, good. All right, so well, you know pretty much as I do on these pseudo distances. So let's move back to quantum dynamics and see how these distances, or this pseudo metric, applies to quantum dynamics, because this was, after all, the title. Okay, good. So here is the first example of application. Suppose that you want to look at the mean field and classical limit in quantum mechanics jointly. Right, so the mean field limit in quantum mechanics was proved by several techniques, BBGKY hierarchies by Spohn in 1980, second quantization techniques with a convergence rate by Roniansky-Schlein in 2009, and many others. But let's say, look at these two examples of techniques to prove the mean field limit. In classical mechanics, it was proved by Brown and Hepp in 1977. by looking at the dynamics, by looking at something that's called the Klimantovich theorem that tells you that, that if phase space points evolve according to the Newton system of ODEs, then the phase space empirical measure is an exact solution of the Vlasov equation, that is the Liouville equation with the mean field potential. Okay, so and the convergence rate in Monge-Kontrovich, oh, sorry, this is should be W2, was obtained later by Dobrushin in 1979. So you have this diagram here, where if n tends to infinity, the horizontal arrows correspond to the mean field limit. So Schrödinger goes into Hartree, time dependent. Liouville goes into Vlasov, right? So that's the Brown and Hepp theorem. Schrödinger goes into Hartree is the Spohn theorem. But we know that when as h bar tends to 0, meaning that if you look at particles whose typical action is large compared to the Planck constant, then Schrödinger goes into Liouville, n particle Schrödinger goes into n particle Liouville, and the Hartree equation converges as h bar tends to 0 to the Vlasov equation. Okay, very good. So we want to know whether these diagram of convergences commute. So, for instance, is the horizontal arrow here uniform as h bar tends to 0? And this pseudo metric is going to help you in proving this, understanding this. I'm still returning to this damned Wasserstein, Monge-Kontrovich. I'm hitting the wrong key here. Yeah, so here it is. Okay, so here I'm writing the quantum n-body Hamiltonian with v real valued plus even, so that the action of particle J on K is minus the force exerted on J by K, and vice versa, right? So Hn is the sum of the kinetic energies of each particle. Then you have the sum of the potential energy, the interaction of Xj and Xk. And here you have a coupling strength, which is proportional to 1 over n, where n is the number of particles, right? Because particles are identical, it's enough to consider particle number 1. And you see here that it's, if you pick j equals 1, it's accelerated by this potential here. If you think of the xk being distributed under the modulus squared of the wave function for the typical particle, well, I mean, you would expect that something like law of large number will tell you that this sum here would converge to v star mod square of psi h bar time t computed at x1 as n tends to infinity. Okay. Now, all that remains to be done is to find a governing equation for this psi h bar, and this is the time-dependent Hartree equation, which is written here. So it's like a Schrödinger equation for a single particle, except that the potential is now the mean field potential, which is a self-consistent potential depending on the solution itself. And you start from some initial data, psi h bar initial. Good. Now, you look at the solution of your n-particle dynamics, and that generates n-particle wave function. So I'm going to start from the n-fold tensor product of the initial data here. So in other words, I take from a factorized, which is bosonic state, right? So that's the wave function is symmetric in all its arguments. So I look at the product from j equals 1 to n of psi h bar initial of xj. So that's an honest wave function of x1, x2, xn. And I'm going to propagate it by the flow, the quantum flow generated by this Hamiltonian here. Okay. Okay, so I do this, and I'm looking at the n-body density operators at time t, which is going to be the projection on this psi h bar n at time t. Now, of course, if initially this thing is factorized, after I propagate it at time t, it's no longer factorized in general because of the interaction which is here, which doesn't preserve the factorization, as you can imagine. Okay. All right, so if I want to extract from this a single particle wave function, what I can do is look at the first reduced density operator, which is the analog of taking the first marginal for probability measures. The way you do this, you look at your r h bar n at time t, you look at its integral kernel. So it's given by psi bar, depending on some variables, times psi depending on other variables written here. And you're going to make the, say, n-1 last variables. So whether you take the last, the first doesn't matter because all the particles are identical. So suppose I take the last, so you take the last n-1 positions to be the same in both wave functions. You integrate dz2, etc., dzn, and you get a kernel in x and y. And here I realized that I should have taken the conjugate here and not there, but it doesn't matter, right? So okay, so it's going to be it's going to map functions of x into functions of y. Not very nice, but that's the way it is. Okay, so that's your now this is an honest density operator in L2. Maybe not a projection in general. It's not a projection, right? But it's a single particle density operator. And here's what you can do with this. So, okay, so for simplicity, suppose that I start with something that's where I take a wave packet, but not a Gaussian one. I take a profile, which is a Sobolev H1 function, right? Scale it exactly as in the case of the Gaussian. I multiply it by e to the I p dot x over h bar. So that's an example of oscillating wave function. A is normalized. I'm going to assume that V as force gradient that is Lipschitz continuous, even. And then for each positive time, I'm going to look at the Wasserstein distance between the UCMI of the solution to Hartree, to the mean field equation at time t, and the UCMI of the reduced density matrix, depending on n, at time t, also take it to the square. And what I'm saying is that with this pseudometric, if you compute the propagation of the pseudometric Gothic H through the n-body problem, then you arrive at an equality that tells you that this quantity here is bounded by the sum of a quantity that is small semiclassically, that is proportional to h bar, of course, grows like exponential to LT, where L is expressed in terms of the Lipschitz constant of grad V by this formula here. And then you have another term, which is small by the mean field limit, because you see that this term is proportional to 1 over n. You would expect perhaps 1 over square root of n, but remember this is a square distance, right? 1 over square root of n will be standard deviation. This is okay. I mean, here we have a distance to the square. So here you have something which is proportional to the sup norm of the force divided by n and multiplied by this exponential amplification e to the LT, the same as here. So it's for you see with this that the mean field limit is uniform as h bar tends to 0, and because you don't have any, so you see that where is it? So the stiffness, right? The fact that you look at time t over h bar, the stiffness in h bar has disappeared in this estimate here. It's taken care of by the fact that you consider the gradient of V and not V itself. I mean, that's how the stiffness is taken care of in this limit. And here alpha is this quantity. I mean, this is the Gothic D distance for this state here with itself, which you can estimate explicitly in this case because it's a rank 1 operator by this expression here. Okay, so I think this is the end of my time. There was another application which is perhaps of interest for the numerical analyst. Maybe I'm going to skip in the interest of time. Nevertheless, I will leave the slides for you to read if you so you wish. I mean, this is again uniform as h bar tends to 0 convergence of time splitting strategies for the von Neumann equation. Okay, so let me jump to conclusions. So here we've defined a quantum pseudometric, which is a deformation of the Wasserstein distance. You can use it to obtain uniform in H-bar estimates on quantum dynamics in the semi-classical setting. In other words, for small H-bar. This assumes very little. You just have to assume the existence and uniqueness of classical dynamics. In other words, you have to assume that the interaction potential as Lipschitz continuous force. You can apply to mean field plus classical limit, to numerical analysis. You can also apply to problems in control theory, especially something that's called observability of solutions. So we have a paper with Thierry, which is going to appear in M3AS. So there are several extensions. In particular, I want to mention an extension to Schrödinger plus magnetic field by my PhD student, Ben Porath. You can also compare classical and quantum densities directly. So in other words, you can extend this Gothic D to the union of classical and quantum densities. Yeah, I want also to mention another approach of the optimal transport problem in quantum mechanics. I already mentioned the one by Trevisan and De Palma. There's another approach which is based on not on couplings like in the Kantorovich formulation, but on the Benamou-Brenier formula, which is something due to Eric Carlin and Jan Maas, which appeared in CMP and General Statistical Physics over the past 6 or 8 years now. Time passes. And finally, here is a list of references used in this talk. Thank you very much for your attention.
So thanks a lot, Francois, for your great talks. So are there questions from the audience? So a call to the participants that you can also write question in the chat.
Questions.
Question, do you see some hand raised?
No, I don't.
Okay, so then I will start. So just a very naive question about the fact that in general, the Wasserstein 2 or Monge-Kantorovich 2 distance has been used a lot, in particular also in the context of gradient flows for parabolic equations. I was wondering whether this kind of quantum pseudo-distance could be used for doing something similar or not?
Yes, I mean that would be very nice if it could be done, right?
Yeah.
But if you look at the definition of gradient flow, for instance, like in the book by Ambrosio, Gili, and Savare, I mean, you use in this formulation of de Giorgi for the gradient flow, you really use the fact that you have a real bona fide metric, right? I mean, the triangle inequality is important there. And here we don't have a triangle inequality. We have triangle inequality up to this, right? So you have this triangle inequality, where is it? So,
factor, square root of.
Yeah, well, up to square root of dh bar. So it's a bit, so this certainly is in the way, right? So if someday we could prove that we have a true triangle inequality, of course, that would be quite different. But I don't know if maybe, well, I don't know, maybe this is in the nature of things, right?
Yeah, it looks so with the, let's say,
well, I mean, what I can say with certainty is that the proof of the triangle inequality for Wasserstein 2 doesn't seem to go through in this case. Well, I mean, this gluing of couplings seems desperate in that case.
So are there other questions?
So Francois, do you hear me?
Yes.
So talking about this triangle inequality that you have right now on the slide. Yeah. So if I don't have just one stop S, but I have a sequence, I'm just thinking of a sequence of stops. So I will start to accumulate all the square root h bar.
Yeah, that's a problem.
So you start losing something. What does it mean? I mean, the lack of uniqueness, because the distance of S to itself is not zero. So this thickness means.
Yes, but you see,
you thought about it.
Yeah, let me say a few words about this idea of distance of S to itself, which is not equal to zero, right? Not only it's not equal to zero, but actually you can compute exactly those for which it's equal to zero, right? Because if you look at your cost here, your cost turns out to be a harmonic oscillator in the variable x minus x hat. So if you want this thing to be equal to 2d bar identity, right? So this is going to be true only you can characterize exactly those things for which this operator reaches its ground state. Okay, and not surprisingly, you're going to find Toplitz operators. I mean, these are the examples which you find. Okay, so for Toplitz operators, you have the Toplitz operators are the most compact points, if you want, the narrowest points for this picture. But if you take wider, if you take other examples, for instance, let me take the example where you change the profile. If you don't have a Gaussian profile like this, you see that you have a constant, which is this quantity here, which multiplies h bar, and this constant can be arbitrarily large, right? But you take A being a H1 function, I mean, this thing can be pretty large, right? So
can you define the distance not for states, but sort of like equivalence class defined by the Toplitz character?
You mean
saying that you cannot identify the distance for this entity, but just up to an equivalence class up to this Toplitz operator?
So you mean you would like to mod out the Toplitz operators? You would like to take
take it out.
You would like to take the quotient of densities by Toplitz operators? That's an interesting notion.
This means that then you cannot approach any given state, sort of situation, any given configuration, but up to the equivalence class period.
Good idea. I've not thought about this. I'm not sure. Yeah, perhaps. I don't know. I mean, this is.
Anyhow, thank you very much. A very nice talk, François.
Thank you. My pleasure. I think that Irene.
Yes.
Irene,
we cannot hear you.
I can't hear you.
Irene, I think you're mute.
Wow, what's going on?
Let's go on. So
there are some questions in the chat.
Yes.
Some questions in the chat. So
yeah, quite a few.
Very bad with the chat. Let me see.
Now there are two by Stefanos Georgiadis.
Where do I see the chat? Oh yeah, here it is. No question. Pas de question ouverte. My goodness. Oh yeah. Wait a minute. Sorry. Okay, so are there any implications of this cheaper formalism to classical problems in the sense that one can use it to improve, obtain new results that have been treated with the formulation of Wasserstein distance, numerically demonstrate equalities or inequalities? You mean by classical problems, you mean problems in classical mechanics? You mean obtaining some inequalities on classical dynamics starting from the quantum Yeah, no, that's I cannot say that this has been done. That I mean, the quantum setting is difficult, so I don't know. But maybe I'm not sure I understand your question, and maybe your question should be understood in a different manner. So I don't know. I mean, this is the answer to Stefanos Georgiadis. Yeah, I think that Irene wants to ask a question, but I can't see her.
Yeah, so I don't see her either. So if there aren't other questions, let's thank François for the great talk.
Thank you very much.
Okay. No, Irene raised her hand again.
Yes, Irene Gamba.
Hi, Irene.
Irene, we can't hear you.
Okay, unfortunately.
Can you hear me?
Okay.
Okay. Great.
Yes.
So we hear you now.
I needed your permission, Michaela. That's what
You don't give permission to Irene, I'm sure.
Yeah, I don't know.
It's strange because other people could talk.
Yeah, that's right.
I'm sorry.
I don't know why it says it came from you. So my question is this, François, can you extend these techniques when instead of just when you take the quantum trace-like operators, but going into what we actually call the breaking of symmetry, that would allow you to link all of these aspects that are most related with the transport part of the quantum mechanics system into the components that would correspond to the, for instance, coupling it to the quantum Boltzmann for Bose-Einstein condensation.
Okay, so
I mean, to do what is called breaking of symmetry, three-point correlations, and I'm thinking that the classical argument that comes from kinetic theory would be more or less how you pass from the endpoint probability distribution functions for continuum probabilities, right, into the derivation of, for instance, the Leonard-Valescu equation, or for weakly magnetized plasmas, right, for things that you can put electric fields. Because there you can actually get some components of metrics, even in the, at least for the space homogeneous, the Monge-Kantorovich metrics may actually work.
Okay, so that's a question. I've of course thought about that when we started working with Clément and Thierry. We of course with Thierry we are very interested, for instance, as to whether we could use these metrics to, for instance, quantify or the rate of convergence of the in the Katz problem, right? For instance,
yeah, that's right.
The derivation. Yeah,
the perfect configuration, like the analog to.
Right, and
condensate and a collision frequency that allows for the.
But you see, yeah, maybe I think at the moment. When I tried to do this, it was like 6 years ago or 7 years ago, and my understanding was not good enough, probably, and I did some very naive things which did not work, right, to cut short. In particular, of course, in these estimates here, the key is to choose a nice coupling, and constructing couplings when you have collision operators, this is a difficult task, right? Yeah. And maybe this is mostly the problem. The problem is that my understanding of what should be a nice coupling, or which kind of coupling to use, is not good enough that I can actually use these distances on it. Because in the end, you know, this theorem 3, for instance,
Yeah.
this is just a type of moment estimate on the solution of a big transport equation where you double all the variables. But at the end of the day, it boils down to estimate the growth of some moment, right? That's all, right? And the idea is that you want to estimate the growth of some moment, but of the solution to which equation? And the solution to which equation? What is a coupling strategy when you have collision operators? This is, I think, a very hard topic, and I think even probably specialists of these questions usually don't consider this a trivial matter at all, right? And
Right.
so,
but there, yeah, we did this work.
For me, who have even much less command, I mean, my understanding of these things is too is almost negligible. So then, yeah.
Maybe
so
that's
I did not succeed. Yeah.
Maybe this is a good thing we can chat when we get together.
Yes, certainly. I would be.
That would be great.
I would find it great if something could be done along these ways.
Right. Okay.
Yeah.
I wrote you late. Okay.
Okay. Very good. Thank you.
All right. Thank you very much. Great lecture.
Thank you, Irene.
So if there aren't other questions, let's thank François for the great talk.
Thank you very much. It was good to see you, all of you.
Good to see you all.